Good morning. Hello, everybody. Welcome to our Crank Embedded UI Live Series discussion for today. Today's topic is going to be memory optimization considerations for embedded graphics. It's a big title. I couldn't fit it all on the title page. So hopefully you'll follow along today and learn a little bit about how memory considerations play a role in your UI configuration for embedded systems. This is a build a little bit on our last session talking about MPUs versus MCUs and the technologies that make MCU a viable choice when you're building your embedded user interface. And we're going to be continuing this and rolling it forward into the next session because it is such a big topic. But we're going to be trying to cover kind of the baseline today of what embedded memory configuration really means and what aspects we want to talk about when we talk about sort of optimizing your system and making some decisions. So we're going to start off today, and the first thing I want to talk about is we've kind of pre-populated my whiteboard, and I'm going to try and stay in frame. We're going to use a lot of the whiteboard today. Talk about the types of memory that we're talking about when we talk about embedded memory configurations. Really, there's two broad classifications for memory. There's embedded flash and embedded RAM. They play different roles in the configuration of your system, and they typically are present in some capacity, in different volumes, for both. Really, the important thing to start off thinking about is what is the nature of flash and RAM? And when we talk about flash memory, what we're really talking about is, persistency. The notion that I've got something that doesn't necessarily can be programmed, doesn't necessarily need to be refreshed, while RAM, when we're working here, is much more dynamic. I'm going to swap out my marker here, just get something that's a little bit darker, a little bit more black. That way you'll be able to follow along. So flash being a little bit more persistent, it's typically where you want to put your data, put your code, and RAM being a little bit more dynamic, tends to be a little bit more expensive. It requires, sort of an ongoing sort of voltage and power to maintain its contents. So, that's sort of the nature of the two categories of memory that we're going to be talking about. Bottom line, talking about performance, we want to talk about access speed. We want to be talking about how fast I can get data into and out of these types of memory configurations. And so, talking about read, generally when we're talking about flash, we're talking about fairly fast access speeds. We're not talking, in the context of a UI in terms of what we need to access for visual performance. Again, we're still talking about milliseconds, right? If I'm showing something at 30 or 60 frames a second, I'm talking about, sort of 15 millisecond refresh rates that I need to be able to access content, compose it, put it out onto the display. So relatively fast. When we talk about RAM, we're talking about very fast. And on the whole, generally we're looking at sort of orders of magnitude in terms of access speed between these two different types of memory configurations. Writing is a whole different ballgame. Because flash is persistent, right? The writing process here tends to be very, very slow. We're not talking about using this as a dynamic store where I'm actively reading and writing content back and forth. So for example, we would not put our frame buffers into flash. But on the other hand, from a write perspective, we're very interested in putting that type of content into RAM because it is also, we'll say, very fast. And I realize that the boxes here are small. Hopefully, you'll kind of just key off the ideas as we're going through here. The writing's not particularly large. Now, given the idea that flash is persistent, but it's a little bit slower, certainly slower for writing, reasonable for accessing the reading content, what do we typically use these two different types of memory configurations for? Well, in the case of flash, I already mentioned, this is really where you're going to put your code, where you're going to put, sort of your data configuration. This is, anything that is, kind of more along the lines of, long-term storage. This is what you want to put into that configuration. Now, RAM, on the other hand, because it's dynamic, because it's fast, what we really want to do here is we're looking at putting in sort of all of the variables that we're going to engage with, right? All of your, kind of read, write content. And, variables is a pretty broad classification. When we talk about your embedded program, there's all sorts of different types of variables that you're using in that configuration. So let's be a little bit more specific, right? We can say, we'd like to talk about our program stack, right? The execution, needs to have some storage space for local variables. We also can talk about heap, right? The heap memory is this dynamic memory that we're going to be using, right? These are all stored in RAM. And, if I bring it back to the notion of embedded graphics and where we're, kind of looking at there in terms of, items that are occupying memory, really, we're also going to talk about the frame buffers. And I told you I was going to use a lot of the whiteboard today, so we're going right to the edges. So we've got the frame buffers, the stack, the heap, the variables. Big topic. We're not going to really explore Flash too much today. We're going to leave Flash as a place for code data and storage of assets as a conversation for our next session. We're going to dive into that in that capacity. We're going to look at it there. Oh, I got someone going here. We're going to dive into it in that capacity. And then what we're going to do is, today we're going to really look at the RAM flow. We're going to look at what goes into RAM and how that's organized and what you can do about optimizing that. Typically, right, if I think about MCU versus MPU configurations, right, when we talk about MPU configurations, a lot of what you're going to do in terms of memory access is going to be hidden behind the operating system, the Linux system, the QNX system, the Windows system. Those are all going to, sort of mask your access into RAM. They're going to localize your memory into a process space. They're going to virtualize it. Really, when I talk about the configurations today in terms of optimization, a lot of this is really MCU centric, right? Where you're building and tightly controlling how your memory is being accessed. So in that case, if this were to be considered my block of heap, right? What we find is, and I'm just going to switch sides here. It's going to be a little bit easier to work my way through this. What we're going to find is that our heap is typically carved up right into blocks for variables. Oh, I'm getting some missed calls here. It looks like everything is going all right. All right, sorry, back on track here. Looks like we're getting some missed blocks. We're allocating blocks in our heap for our variables. And then what we're doing is, the linker is going to also allocate, larger blocks here for your stack. Now, what's the role of the stack? The stack is where you're putting all of your local variables, right? This is where when your program is executing, you're going into functions, those variables need to be stored somewhere and put somewhere. So that's what the stack is for. And then typically, we're going to have a larger chunk left over, and we're going to allocate that for the heap. Now, this is an MCU type configuration where everything is tightly packed together. What's really great here is that the linker is doing this tight packing for you. One of the challenges working with embedded systems is you want to be able to maximize the value of the resources that you have. So if you know in advance how how much space your variables are going to require, your stack is going to require, all those things can be pre-allocated in advance, right? And they can all be tightly packed together into, what is really our block of RAM. So if I dive into, what our code is going to look like here, if I look at what our code is going to look like in terms of the system configuration, what I see is that these stack blocks, right, are going to get used in a very efficient manner. They are much larger, right? These variables might be, an integer here, an integer value there. These stack areas tend to be larger blocks of memory. And so in our stack configuration, what we can do is we can actually look at how that execution runs. So typically our stack, just like it sounds in terms of computer science terminology, our stack is a block of memory that kind of accordions up and down. So initially, right, when you call your program, there's going to be a certain amount of memory allocated for the local variables inside main. As you call out into new functions, so in our case, we have this f1, we need to allocate space for that function for those local variables somewhere, right? Where is that int a being defined? So now what we can do is, we can put that memory temporarily on the stack, allocate it. We grow our stack up for the duration of that function call, and then when we return, the stack memory usage is going to drop down again. And then as we go and call another function, so in our case, our f2 function, what we'll see here is we're going to go and reuse that space for the new variables. And so there's an overlap here, and that's why, one of the challenges we have working with embedded systems, of course, is, we're always looking at static analysis, we're looking at, sort of provability. What happens when a C developer returns the address of a variable on the stack? Well, they're pointing at this memory, and this memory is going to be rapidly reused, right? So you always have to be kind of aware of, sort of the variables that you're using and the addresses that are coming from that use and how it's being propagated. Okay to use this address, going up the stack for the function calls, not okay to use it going down the stack as you kind of call back out of those functions. So F1 and F2 here, sharing the stack, but very efficiently, right? Again, this memory is going to collapse back down to just the main as you kind of accordion in and out, right? As you recurse in and out of your call tree. So stacks really don't offer much of a concern in terms of they are a pre-allocated amount of memory, and you always have to, kind of consider what your maximal usage is going to be. However, they are very effective in terms of, sort of general management of memory. Not a lot of concern there about long-term fragmentation. So let's take this off the board here, and let's take a look at a different scenario now. I'm going to run a different scenario now, and I'm going to look at heap usage. So heap is really what is underlying your malloc calls, your free calls, your calc calls, your dynamic memory allocations, right? Those all come and take place out of the heap. Now there's lots of different policies and ways in which the heap can be managed. Today I'm going to talk, kind of in a general sense of what this looks like. But what we can imagine is that this heap, is kind of a continuous block of memory, and it gets broken down and subdivided into two main types of uses, right? We can kind of, we'll arbitrarily kind of split down the middle here. On the one hand, you have what's called a small block allocator. And the idea of a small block allocator is that you want all the efficiency that you would see with a stack, right? Very deterministic. We just, kind of allocate blocks of memory and we pull them out. And this small block allocator typically ends up being sort of a power of 2 subdivision of blocks of memory. So what we might have is, for example, a whole set of memory carved into bins of 8 bytes each, then a set of bins at 16 bytes, and then a set of bins at 32 bytes. This way, when I make an allocation, if I'm looking for 5 or 6 bytes, I'm going to allocate out of this bin block of 8. So there is a little bit of wastage, there's a little bit of overhead, but the benefit is that I'm very deterministic in terms of my access time. I'm very rapid. I can get into it very fast. I don't have to do a lot of lookup and calculation. I can sort of jump to the right bin size based on the allocation request. And there is going to be a little bit of wastage if you're not hitting the bin size directly. But frequently these can be tuned for your application, right, these allocators. Similarly, you don't end up with any sort of fragmentation. All the bins are the same size, and so your wastage, right, that extra little bit of overhead, is a trade-off against not ever sort of losing access to blocks of memory. That's on the small block allocator side. Let's transfer over and look at the big block allocator, right, the other half of this memory. So, this might have been, if I had a 200K block of memory, maybe what I did was I took 8K and I put it over here in the small block allocator and I divided it up. And maybe what I said was I want to leave the other 192K over here, and I'm going to use those for arbitrarily large allocations. And 192K, that seems pretty reasonable. I can put some frame buffers in that space. So I might see, For example, an allocation that comes out of this as 64K, another allocation of 64K, and you can see these, sort of coming out in our little kind of diagram here. But what happens with this memory when I start freeing blocks, right? So if I allocated first and then second, and then I deallocated the first block, I've got this 64K, hard to read there. I've got this 64K and 64K block sitting here on the side, but now I want to make an allocation for 128K. I'm stuck. I have it available, but I can't access it because I've got this block in the middle. And this is what, when we are concerned about fragmentation of memory, right? This is the downside of working with dynamic memory, is that when you make repeated allocations and deallocations, depending on the life cycle around those allocations and deallocations, you run the risk of fragmenting your memory, breaking it up into unusable chunks, especially when we're talking about large allocations. So this is the notion behind really trying to pre-allocate as much as possible and put that put that allocation up front. And then if you know the allocation patterns of your system, you could further subdivide these and put them into your own custom block allocator. Right? Maybe your small block allocator can't fit that, but this is something that you can design for your own particular embedded system. Frequently a technique that's used. So let's get rid of these little overlays here. So the last piece that I'd like to talk about is a lot of our embedded systems are not working with just one contiguous block of RAM. A lot of times, what we're going to find is, especially in the MCU space, we will have several different types of blocks of memory. So I might have one block of memory here, maybe it's 128K in size, and it's fast. All right, and I'm going to use the terms fast and slow because there's lots of different types of RAM, there's lots of different types of flash, each with their own characteristics. But this second block of RAM, here, it's available to me as well, but maybe it's more voluminous. We have 256K of memory available here, but it's a little bit slower, right? So I'll just say faster and slower in this case. What do we want to do with these two blocks of memory? How do we want to allocate our resources? Well, we know for sure, right, it's always better to use things that are fast. But if we have a system that can't fit entirely into this 128K, what do I do and how do I make choices about what should go where? Well, the rule of thumb is what's fast should be something that you're going to access frequently, something that you're going to be reading and writing from repetitively, right? So you're going in and out, and you're going in and out a lot, right? So stack falls into that category, right? Your heap can fall into that category as well in some capacity. But we're embedded UI developers, so we're going to talk about frame buffers. Frame buffers are really just large contiguous blocks of memory, right? They can come from the heap. They can't really come from the stack, but they can certainly be defined as global variables. So if you have the opportunity to look at these classifications of memory blocks that you have, and they're not contiguous, so you have to do a little bit of shuffling. If you can allocate your frame buffers from these and make choices, then you can use the information about the speeds and the characteristics of what we're going to be rendering to your advantage. And what I mean by that is, typically when we're rendering to a display, our frame buffers, it's not a single frame buffer. It's not a one frame buffer to the LCD display, that you've got a mapping. If you did that, every time you composed a scene, right? So here's my blank display, and now I'm going to compose a scene that's going to be filled, blue rectangle here, right? And then maybe what I do is I compose and put an image with transparency on top of that blue rectangle. If my system is fast enough, maybe I won't see the artifacts. But generally, I don't want to see the composition stages of the image. I'm only interested in seeing the end result. So this is where we get into various methods in which we flip the buffers that we're drawing to onto the display. It's a whole other topic for another day in terms of the different techniques that we can use, but we have choices. So this is, we'll call this frame buffer 1, and this is frame buffer 2. Typically, we'll draw to one frame buffer off screen, then we'll flip it on screen and take the other frame buffer and start drawing to it. Now, there's lots of different strategies for doing this. Back buffering, double buffering, triple buffering, multi-buffering, lots of different ways to approach this. But our goal is that when we go to the display, rather than seeing all the individual scene elements, we just show up with the composed element, right? Here's my awesome graphic. So if we look at what we're doing with these allocation patterns, the off-screen buffer, because it's being composed to, is going through a lot of read, write, read, write, read, write cycles. I need to access this buffer to draw the initial content, then to read it back and compose in overlay content. I might do that many different times. But if this is my primary buffer going to the display, I really only need to write that once. So if we look at how we might use this type of RAM configuration, make some decisions about which buffer should go where, really we want this buffer with its frequent read-write access to go into this fast buffer area, right, if we can make it fit. And then ideally, if we can make them all fit, we put them all into the fast buffer, but it might be a very acceptable trade-off to put this buffer into the slower access area, because we're only going to write to it really once, and then the display will access it. Here, maybe by putting this buffer in here, we segment it and we give ourselves a little bit of access space for stacks, right? For some other variables that we want to access more frequently, right? So it's an important consideration for how we use the memory. So in summary, lots of different things to know about embedded memory, lots of different kind of considerations. Next session, we're going to talk about how you compose a very rich UI without really running into this fragmentation issue, having to leverage the heap and the dynamic memory allocation, being able to pull content directly from Flash, and being able to encode our images and our font data directly into storage, which is slow to write, but fast to read, at least fast enough for our embedded user interfaces. That leaves us with the ability to leverage the RAM, which is very fast for both reading and writing, for things like our frame buffer and our composition store. I'm going to take a quick look and see if there are any questions here. It doesn't look to me like we've got any questions. Sorry, there is a question. Where should I put the frame buffer, SRAM or SDRAM? I think you were probably a little bit ahead of me on that question. I like to think that we've answered it here. It's not necessarily a question of one or the other. It's really a matter of taking a look at your access patterns, right? So if you can put your back buffer into your faster RAM, so that would be your SRAM, not your SDRAM, and then your primary buffer into the SDRAM being slower than your SRAM, then that's what I would recommend you do. Now, in our next session, we'll be talking about Flash and data storage and images. But in between these sessions, if you have questions, we're always monitoring our YouTube channel. You can always ask questions in there, and what we'll do is we'll try and carry those questions forward into our next sessions, and try and do a little bit of Q&A on the fly as it is. There is a bit of a sequencing that we're going through, and there are several sessions that we're going to go through to work through all these different topics. One more question here: how much stack and heap do I need to allocate? Peak versus steady state. That's an excellent question. The answer is generally you always need to allocate your peak, if you're thinking about stack, because the challenge is that if you don't allocate for your peak, you run the risk of a stack overflow at some point in time during your execution. The steady state operation may be much lower, but these are the type of things that you want to analyze during your execution and say, well, are there ways that we could actually mitigate that high cost? Maybe what you've got is you've got a heavily recursive function which forces your stack usage to go high, but it's an unnatural kind of growth. You could turn that into more of an iterative approach where it's a little bit more linear and your stack growth isn't going to go out of control, and then that lowers your overall footprint. Most embedded operating systems offer us various tools by which we can kind of scribble into the stack in advance, and then run our programs and actually take a look and see, how far did we get up, what was that high watermark. So I think we're done with the questions for today. Thank you very much for your time, and I look forward to talking to you in our next session. Thanks.